Okay, so hello everyone. Good evening.
Evening, ma'am. How are
Good
you?
evening, ma'am.
Yeah,
Good evening,
good.
ma'am.
Okay, so everyone has joined except Zunaira, Zanab, Neha, Aman, Aisha, Saniti. Okay, so let's not wait. Okay, so have you guys revised the topic?
Yeah, ma'am.
Any doubt?
No, ma'am.
So let's just start. So equilibrium reaction. Equilibrium, there are two types of equilibrium reaction. First one is your homogeneous equilibrium reaction, and the second one is your heterogeneous equilibrium reaction. So let's understand what is the difference between these two terms. Homogeneous means homo means same, identical, right? And hetero means different. So homogeneous equilibrium reaction are those reactions in which all the species are in the same phase. Okay, the state of all the species are same. For example, consider this equation. Okay, this equilibrium equation H2, okay, plus carbon dioxide. So it will give you H2O plus carbon monoxide, CO. Right, so here you can see all the species are in the same phase, which is in gaseous phase. Okay, H2 gas, carbon dioxide gas, it is again in the gaseous phase, water vapor, carbon monoxide is again the gas. So if all the species are in the same phase, so we can say that this equilibrium reaction is homogeneous type of equilibrium reaction. Is it clear?
Yes.
Yeah, ma'am.
Similarly, the second one is your heterogeneous equilibrium reaction. So heterogeneous equilibrium reaction are those equilibrium reaction in which species are in different phase. Okay, you can see the example calcium carbonate, okay, which is in solid form. But when it dissociate, it will form calcium oxide plus carbon dioxide. So carbon dioxide gas, dioxide over here is in gaseous phase, but other things like CaCO3 and CaO are in the solid phase. So here you can see there are two different phases, solid as well as gaseous phase. So this type of equation or equilibrium reaction are known as heterogeneous equilibrium reaction, where the species are in different phases. Is it clear?
Yeah, ma'am.
Yeah, ma'am.
Yes, ma'am.
Yes.
Ma'am, I have a test on December 7th for thermodynamics, equilibrium, and redox reactions. These are chapters coming.
Okay, redox reaction is also coming.
Yes.
And one more thing, Aman, you have your exam, right? What is the date?
Yes. Which one?
I think organic chapter is coming, organic chemistry.
Yeah, yeah. Organic chemistry.
Okay, so we have to complete two chapters after the equilibrium, redox as well as the organic. Okay, so Sanidhi, redox reaction, right? And you're for Aman, we have to complete the organic chapter. Okay. So
Yeah.
we have to move in a very fast mode. Okay, Sanidhi, if required, so we can take some extra classes of yours.
Okay, ma'am.
Okay, so in which I will complete the redox reaction. So reaction quotient. So reaction quotient. So let's understand what do you mean by reaction quotient, which is denoted by capital Q. So expression like equilibrium constant. Equilibrium constant is denoted by Kc, right? So expression like equilibrium constant, whether the reaction is in equilibrium or not, right? So this reaction quotient is that question is just like a equilibrium constant. But the difference is that equilibrium constant is for that reaction or equation where the reaction is in equilibrium, right? Where the reaction is in equilibrium, then only we can use this term AC, equilibrium constant. But the reaction quotient is used whether the reaction is in equilibrium or not. Okay, the reaction can be in equilibrium or it may not be in equilibrium. Both the cases is possible for the reaction quotient. But for the equilibrium constant, Kc, okay, always remember the equilibrium should be maintained. For equilibrium, we use the Kc only for equilibrium reaction. But for reaction quotient, okay, if the reaction is in equilibrium or if it is not in the equilibrium, we can use the term reaction quotient for that reaction. So that is the difference between the reaction quotient and the equilibrium constant. Is this clear? What is the difference
Yeah,
between these two? Okay, so suppose this one. See, we will write down the same thing for the Kc as well as the for the Q. But the difference is here for the Q, we just write down the same thing. Just जैसे हम लिखते थे like Kc में for the reaction expression. For example, just a second. Suppose if we take A, okay, AA plus BB, okay, CC plus DD. So how we can write down the expression, equilibrium expression? So Kc will be equals to the concentration, okay, the product concentration raised to the power C, okay, the stoichiometric coefficient of it, multiplied by capital D raised to the power D upon the reactant, the concentration of A raised to the power small a, concentration of B raised to the power small b, right? So similarly, we can write down the expression for the reaction quotient, right? So similarly, we will write C D, concentration of D raised to the power D, concentration of A raised to the power A, concentration of B raised to the power B. But the difference is that in the Kc, when we talk about the Kc, when we write down the expression for the Kc. So it is always necessary that the concentration of A, B, C, and D are equilibrium concentration. The concentration are at equilibrium. But if we talk about the Q, if we talk about the reaction quotient, right? So it is not necessary that these concentration are at equilibrium. It can be at equilibrium in some conditions. Okay, it cannot be at equilibrium. Okay, so both the cases are possible if we are writing the reaction quotient. But if we are writing the Kc, this expression, so it is always compulsory. So it is known that all the concentration, whether it's reactant concentration of the reactant and the concentration of the product, all are equilibrium concentration. All are at equilibrium. That's the difference between these two. Okay, but the expression looks same. Okay, you will write down the same expression. Is it clear?
yes. Yeah, ma'am.
Okay. Now see this. So suppose AA, this is the general equation. So how we can write down the reaction quotient? So Q will be equals to the concentration of C raised to the power C, which is the stoichiometric coefficient. Okay, and so on like this. And here the concentration of A, B, C, and D are not equilibrium concentration, right? Are not equilibrium concentration. But at equilibrium, when the reaction is at equilibrium, so the Q will be equals to the Kc. The reaction quotient is always equals to the Kc at equilibrium. Okay.
Yeah, ma'am.
Okay. Okay, first write down till here. Write down till here, then we will proceed. question, everyone?
Yeah, mom.
Okay, now see the applications of equilibrium constant. What are the applications of equilibrium constant? First application is the prediction of extent of reaction. Prediction of extent of reaction means whether the reaction will occur in the forward direction or in the backward direction, right? Means whether the reactants will dominate at equilibrium or product will dominate at equilibrium. Which one is more stable? So we can predict the extent of reaction using the equilibrium constant. Okay, suppose we have a K. This is K equilibrium constant. So there are three cases here. There are three cases. Concentrate over here and try to understand these concepts. First case, first, this is K, okay, equilibrium constant. So first case is where the Kc value is less than 10 raised to the power minus, okay. The equilibrium constant value is less than 1 upon 1000, 10 raised to the power minus 3, right? Very less value. So here in this case, so always remember reactants will dominate at equilibrium. Reactants at equilibrium when the reaction, okay, reaction reach at equilibrium, the reactants always dominate at equilibrium. And at equilibrium, reactant is more stable. Reactant is more stable. So if the reactant is more stable and if reactant dominate at equilibrium, so the reaction proceed in a backward direction, not in a forward direction. If forward direction में अगर move करेगा, so the product will dominate. Product will dominate over the reactant. But now here, when the Kc value, the reactant, your constant value, equilibrium constant value is less than 10 raised to the power minus 3. So here, in this case, the reactants will dominate. And if reactant will dominate, the reaction will proceed in a backward shift, backward direction. Okay, and how you will show the direction? You will show like this. The symbol for this backward shift or backward direction in this case, you will see, you will show like this. Backward shift, okay, large arrow of backward shift and the small arrow of the forward shift, just like this. Okay, so this shows, this symbol shows that backward shift, backward reaction dominates over the forward reaction. At equilibrium, this backward shift, backward direction dominates, means the reactant dominate at equilibrium over the product. And in this case, always remember the reactant will be more stable. The reactant will be more stable. And this reaction hardly takes place. This type of reaction hardly takes place. This backward shift, backward your reaction, right? So this is the first case. Is it clear? First one,
Yes, mom.
everyone? Okay. See the second one, second case. Okay, first let's discuss the third case. Okay, it is just opposite. First case was when the equilibrium constant is less than 10 raised to the power minus 3. But here, if the equilibrium K value, K is greater than 10 raised to the power plus 3. K is, the K equilibrium constant is greater than 10 raised to the power plus 3, right? That's value. So here the product will dominate at equilibrium. Product will dominate at equilibrium if K value, the constant value, is greater than 10 raised to the power plus 3, greater than 1000. Okay, so in this case, product will dominate at equilibrium. And if product will dominate over equilibrium, there will be a forward shift. There will be a forward shift in the reaction. Means the product is more stable and you will see a forward dominating reaction. Forward shift you will see. Product will dominate over the reactant. And in this case, you have to show and you have to represent by using this symbol. Okay, this large arrow for the forward shift and this is small one for the back shift. So it shows that the forward shift dominates over the backward shift. The forward reaction means the product dominates over the reactant. So this symbol से आप show करो. And here basically, this reaction goes for the completion. When the forward shift or forward dominates over the backward, okay, so here the reaction will proceed and the reaction goes for the completion, okay, and this reaction can happen regularly on a regular, it takes place, okay, in actual life, it takes place, this reaction, but this reaction, backward shift, this reaction hardly takes place. So that is the difference between these two. So the value of K is very important, right? The value of equilibrium constant is very important. It will help you to predict the extent of reaction, which one is more dominating, which one is more stable, and it will show or it will represent basically the means the reaction will shift in which direction, forward direction or the backward direction, right? Now, in the second case, B case, when the K value, equilibrium constant value is between, okay, it is between 10 raised to the power minus 3 and 10 raised to the power plus 3. Okay, means it is greater than 10 raised to the power minus 3, but it is less than 10 raised to the power plus 3. So if it is in this range, the constant value is in this range, so both reactant and product are present in appreciable amount. Okay, both are present, both will be present, no one will dominate over here. Okay, no one will dominate over here, both are present in a much appreciable amount, right? So first one. Second one, both R and P are stable. Both the reactants and products are stable. And you will see, you will represent this type of reaction using this symbol. Both arrow should be equal. Okay, you can see both arrow are equal. It shows the equality basically, right? So that these are the three cases which helps you to predict the extent of reaction. Okay, clear to everyone? Any doubt in this?
No, ma'am.
No, ma'am.
Okay, now quickly write it down. Written, everyone?
1 second, ma'am.
Okay.
Done, ma'am.
Okay, suppose we have this question. A plus B, okay, it will give you C plus D. And the Kc is 10 raised to the power 15. Now tell me which one is more stable, A, B, C, or C and D?
Is it C and D?
Okay, anyone?
Option D.
Option B. Okay, Anidhi? Aisha, according to you, which one is correct?
Ma'am, I also think it's option B.
Okay, so why? What is the reason? What is the reason behind C and D? Why it is more stable?
Ma'am, because the concentration of the product C and D is higher.
Okay, why the concentration is higher? See, each and everything depends
Kc.
on Kc.
Yeah.
Kc is equals to 10 raised to the power 15, right? So Kc is equals to 10 raised to the power 15. It means that K, you can see the third case. The value of constant, okay, equilibrium constant is greater than 10 raised to the power 3. So here it is, K value is 10 raised to the power 15, which is greater than 10 raised to the power 3000, right? So in this case, product dominates at equilibrium and product is more stable. Okay, means the reaction is forward dominating. So in this case, C plus D, which is a product here, it will be more stable. So that's why your D option is okay. Now, second application. So we are just doing the application. First application was it helps in the prediction of extent of reaction. Second is it will help you to predict the direction of reaction or equilibrium. Suppose we have A, okay, A case in which Q is less than K. There is a slight difference between the K and Q, you know very well. Okay, Q is the your quotient, right? And reaction quotient, and K is your equilibrium constant. So when Q is less than K, then it will be a forward reaction. Just remember that. When Q is less than K, and you can also say it like that, K is equilibrium constant is greater than your Q, okay, your reaction quotient, then it will be a forward reaction. Forward reaction means the product will dominate, means the concentration of product will increase, right? So here product will increase and the reactant will decrease in the forward reaction. Okay, so generally हम क्या कहते हैं, the in the any reaction which is forward dominating. Okay, so in a general reaction, like if we are not talking about the equilibrium reaction, just a general reaction. So we just say that the concentration of reactant always decreases and the concentration of product increases, right? So just like that, in a forward reaction, if we are just talking about the forward reaction, so concentration of product will increase and the concentration of reactant will decrease. Okay, so this is the first case when K is greater than Q. Second case is when Q is greater than K. Then in this case, it will be a backward reaction. Backward, there you will see the backward shift in the reaction. And if you see the backward reaction, it means that the reactants dominate over the product. Okay, so concentration of reactant will increase and the product will decrease, right? So this is a backward shift, backward reaction. Third one, third case is when Q is equals to K. When Q is equals to K, equilibrium is achieved. Okay, what does it mean? As I told you earlier also, at equilibrium, Q becomes equals to the K. Okay, so Q is equals to K, so equilibrium is achieved, and at equilibrium, you know very well, the concentration of reactant and product are constant. They are not equal. Constant does not mean that they are equal. The concentration are equal. Okay, concentration may be equal, but it is not compulsory that concentration is equal at equilibrium. Concentration will be constant, will become constant. Okay, at equilibrium, when the reaction achieve equilibrium, at that point, the reactant concentration and the product concentration, they become constant. That what it means that. Okay, so there are three cases again for the prediction of direction of reaction or equilibrium. Is it clear?
Yes.
Yeah, ma'am.
Okay, quickly note it down, this question and the prediction. Then we will do some question based on that. Okay, now see the question. Question is the value of Kc for the reaction, this reaction 2A, okay, which will give you B plus C, is 2 into 10 raised to the power minus 3. Okay, so the value of equilibrium constant is given in the question. At a given time, the composition of reaction mixture is this. Okay, at a given time, the composition of reaction mixture is concentration of A is equals to the B is equals to the C. All the concentration are same, which is equals to the 10 into 10 raised to the power minus 4 molar. In which direction will the reaction proceed? Okay, I will give you 1 to 2 minutes. Just analyze this question and try to do this by yourself first. That's very easy. Anyone? Okay, let's see. This is very easy. See, the reaction is 2A B plus C. Okay, and here for this reaction, the value of Kc is given 2 into 10 raised to the power minus 3, right? It means that what is 2 into 10 raised to the power minus 3? 2 upon 10 raised to the power 3 means 1000. So it will give you 0.002. The value of Kc is 0.002. Now find the Q value. Reaction quotient. Q. How you will write on the Q expression? Okay, so similar, the concentration of B multiplied by concentration of C upon concentration of A raised to the power 2. That is the Q expression. Now you can see here the concentration are given. Okay, for each and A, B, and C, the concentration is same. Now substitute the value 3 into 10 raised to the power minus 4. Okay, multiplied by 3 into 10 raised to the power minus 4. Okay, in the denominator, the concentration of A is also same. 3 into 10 raised to the power minus 4 square. Now you can see this will, this, okay, it is a square, and the on the top, okay, in the numerator section, it is again the square. So you will get 1. It is the value of Q. Q will become 1. Q is equals to 1. Now check the value. Kc, your Kc is 0.002, okay, and your Q is equals to 1. Okay, now see here. What are the conditions? When the Q, see, B case, Q is greater than K. K is 0.002 and the Q is 1. So which one is greater? Obviously the Q. So if Q is greater, here you can see Q is greater than K. So if Q is greater than K, the reaction will proceed in backward direction. Will proceed in backward direction. Okay, so that's how you will solve this type of question. Is this clear, this question?
Yeah.
Yes.
Yes.
Okay, quickly note down. Written?
Yeah, ma'am.
Okay. Now moving to the next question. Okay, see this question. A mixture of 1.57 mole of N2, 1.92 mole of H2, and 8.13 mole of ammonia, NH3, is introduced into a 20-liter reaction vessel at this temperature, 500 Kelvin. At this temperature, the equilibrium constant Kc for the reaction, this is the reaction, okay, the Kc is 1.7 into 10 raised to the power 2. So question is this reaction mixture at equilibrium? If not, what is the direction of the net reaction? Okay, getting the question? Now, okay, so first, let's write down the concentration. What is the concentration given? So here, the concentration of N2, okay, concentration basically we will talk about the molarity over here. Okay, because here we are just talking about the mole per liter, and mole per liter is molarity. molarity, right? So concentration here, we will take the molarity. So the number of mole of each and every component is given, okay? And the volume is again given. So how we can calculate the concentration? Molarity, so the given mole, number of moles, 1.57 for the N2 divided by the volume, right? 20 liter. Okay, so just calculate it and note write down here. And similarly for the H2, concentration of H2 will be number of mole 1.92 in 20 liter. Similarly for ammonia, it is 8.13 divided by 20. Okay, just quickly, just calculate it, divide it. So basically it will give you 0.0785. Okay, molar. 0.096 molar. Similarly, for ammonia, when you divide this, so you will get 0.4065 molar. So that is the concentration. Now see this reaction. The reaction here is, okay, I'm writing here. The reaction here is N2, okay, which is in gaseous phase, plus 3H2 will give you 2NH3. Okay, 2NH3. This is the reaction. Okay, now write down the Q. From this reaction, write down the value of the expression, Q expression. Okay, reaction quotient expression. How you will write? Yes, Aisha, tell me. What will be the reaction quotient expression for this reaction?
Concentration of N plus concentration of H.
In the numerator, we just take the concentration of product first.
Oh, sorry.
Product divided by your reactant, right? So product is ammonia. Concentration of ammonia raised to the power 2
2.
divided by concentration of N2, okay, multiplied by the concentration of H2 raised to the power 3. Okay, here the power is, coefficient is 3, so I have written. Now we know the concentration of each and every term. Just substitute this and just solve it. For ammonia, what is the concentration? 0.4065 square. For N2, it's 0.0785. Okay, multiplied by H2, 0.096 cube. Okay, just quickly solve it. Okay, so when you multiply this, when you take the square of this one, yes, Anidhi?
Ma'am, 2380.4.
Final answer 2380.4. It's a final answer, the value of Q, right? Okay, so let's check it out. So when you multiply this 0.4065, so it will give you something 0.1652. Okay, and this will, when you multiply this, just take out this cube of this one, 0.0785 multiplied by, you will get 0.000884, right? Now just multiply these two. Okay, I'm writing here 0.1652 divided by 0.000069, right? Okay, now just remove this decimal and decimal. Okay, so you will get 1652, okay, divided by, this is 69, Okay, multiplied by. So when you just remove this decimal, so there will be in the denominator part, it will be 1, 2, 3, 4. And here you will get 4 zeros, say 4 0 cancel out. So you will get 1659, 1652 divided by 69. So basically it will give you something 23.94 multiplied by your 100, right? So something you will get 2394.2. Okay, this is just an approximate value. Okay, so you can take this, you will get 2394.2, 9394.2. So you can take the approximate value. So Q will be approximately equals to the 2394. Okay, so Nidhi, so your answer was very much close. Okay, it's 2380. So this is your answer, the value of Q. This is the value of Q. Now compare the value of Q with the K. What was the value of K, which is given in the question? It is 1.7 into 10 raised to the power 2. Q is this, and the value of Kc is 1.7 into 10 raised to the power 2. It means 170. Now just compare this. 170 is less than 2394. So again here also Q is greater than K. Q is greater than K. Means this reaction is not at equilibrium. Okay. Question was, is this reaction mixture at equilibrium? So no, this reaction mixture is not at equilibrium. The direction of the net reaction will be backward direction. Why backward? Because Q is greater than K. Q is greater than K. So this reaction will proceed in the backward shift. Okay, is this clear?
Yes.
Yeah, so this is application based question. Based on the application, they can give you this type of question. Okay, now quickly just write it down.
Done, ma'am.
Okay. Okay, see, the next question is very much similar. Just try it first. Just scroll. Equilibrium constant value is given for this reaction, and you have to check whether the reaction is in equilibrium or not. If it is not at equilibrium, then in which direction does the reaction tend to proceed to reach the equilibrium? Okay, just quickly do this. Try this question. Yes, anyone? Yes, Janab, tell me the answer. In which direction the reaction will proceed? No one?
Uh, Ma'am, forward.
Forward direction. How? Can you explain, Sanidhi?
Ma'am, I didn't tell it.
You just guess.
No, I didn't tell it. That's not me.
Okay, okay. So it was, I think, Zainab. Zainab, you told the answer. Can you explain why you said forward direction? Aman, can you tell me? Neha,
Ma'am, because Q is less than K.
Q is less than K. Yeah, very good. Okay, so you can, this is your reaction. That is very much similar to that, the above question, right? So this is NH, this is your reaction. Okay, N2, first always write on the reaction, N2 plus 3H2, which will give you 2 moles of ammonia. Okay, so the value of Kc is given 0.061. Okay, now the reaction mixture. The concentration over here is given. Okay, no need to find the concentration. Here the concentration is given in the molar. Okay, basically mole per liter. Molarity is given, right? So N2, your H2 and NH3. So first write down the Q expression. Q will be equals to the NH3 concentration raised to the power 2, concentration of N2 and concentration of H2 raised to the power 3. Now we have the concentration. Okay, just substitute it in this equation. 0.5, okay, square. Then we have N2, 3 mole per liter. 3 into what is H2 concentration? H2 concentration is 2. Okay, so can we write 2 cube? So just 0.5 into 0.5. Its calculation is very simple. It will not take much time. 2 cube is 8. Okay, and this will give you 0.25. 8 threes are 24. Okay, so just 0.25 divided by 24. So it will give you something 24. 24. Just a second. Yeah, so when you multiply this 0.25 upon 24, so it will give you approximate value. I'm just writing 0.01. Okay, just approximate value. So here the Q is approximately equal to 0.01 and the value of Kc is 0.061. Okay, so here you can see Kc is greater than Q. If Kc is greater than Q, right, so the reaction will be forward. The reaction will proceed in the forward direction. That is very simple. So for this type of question, first try to find the, sometimes Q value will be given in your question. Okay, and you have to find the Kc. Okay, that's very simple. So find the Kc value and just compare the Q value and the Kc value. Okay, if Q is greater than Kc, then it will be backward direction. The reaction will proceed in the backward direction. If Kc is greater than Q, then it will be forward direction. If both are equal, then it is at equilibrium. Okay, if in your exam they ask you to check whether the reaction is at equilibrium or not, so you have to check, you have to compare the value of Q and Kc. Okay, suppose in this question, if I got Q value, Q is equals to means approximately equals to Kc value, right? So here this reaction will be at equilibrium. Okay, if Q is equals to Kc, the reaction will be at equilibrium. And if it is greater than, Q is greater than Kc, so it is backward reaction. If Q is less than Kc, then it is forward reaction. Yeah, so these are some application based questions which are very important. Okay, now quickly note it down.
Ma'am, these type of application-based questions will come for 2 to 3 marks.
Yes, they can ask you this type of application-based question. I will give you some more questions in your homework. Please try to do those questions. Okay, so the next one, type 2 numericals. So first type we have done, in which data will be given. Okay, first type of numerical was the data of equilibrium should be given. Second type is when the initial data and some hint about the equilibrium is given. Okay, so type 2 numericals. So here, just write down the first question. Question number 1 is, at 700 Kelvin, equilibrium constant for the reaction, and the reaction is H2 plus I2. Okay, it will give you 2HI. Okay, so that is the reaction. Okay, and here for this reaction, equilibrium constant for this reaction is, okay, this is continuation, 54.8. If 0.5 mole per liter of HI is present at equilibrium, at equilibrium at 700 Kelvin, then what are the concentration of H2 and I2? Assuming that we initially started with HI and allowed it it to reach equilibrium at 700 Kelvin. That is the question. Question is at 700 Kelvin, at this temperature, equilibrium constant for this reaction is 54.8. Okay, so if 0.5, this concentration of HI is present at equilibrium, okay, at equilibrium at 700 Kelvin, then what are the concentration of H2 and I2? Assuming that we initially started with HI and allowed it to reach equilibrium at 700 Kelvin. Okay, what does this mean? This line means, see, this line carefully again, read this line. What are the concentration of H2 and I2? Assuming that, we have to assume that we initially started with HI. We have initially started with HI. And what is HI over here? HI is the product. If you consider this as a forward reaction, so HI is the product here. But in the question, it has mentioned that you have to assume that initially you have to start the reaction from HI. So what does this mean? It means that the reaction is proceeding in the reverse order, backward direction. The reaction has been proceed in the backward shift because we have to assume that initially the reaction has been started with HI and allowed it to reach equilibrium at 700 Kelvin. Okay, so now let's see how to do this question. How to do this question. So, solution. So what is the value of K? K value is given 54.8. Okay, the equilibrium constant, which is Kc. And the concentration of HI at equilibrium is 0.5 mole per liter, right? Now see, just note down here, note down. Suppose we have for this reaction A, okay, A is changing into a B. Okay, suppose this is a forward reaction, right? So how we can write down the value of K expression? So K will be equals to, okay, the concentration of your product, which is B over here, upon the concentration of, okay, for this reaction. Now, for reverse reaction, suppose if you reverse this reaction, for reverse reaction. So reverse reaction क्या हो जाएगा इसका B, okay, it will changes to A. That will be the reverse reaction. And for the reverse reaction, what will be the rate equation, rate expression? How you will suppose this is your K. Okay, this is for the normal general equation. Okay, forward reaction. And for the backward reaction or for the reverse reaction, suppose it is K dash. Okay, K dash. So how you will write on the expression? It will be the concentration of A upon the concentration of B. Are you getting my point? Yes or
Yes.
no? So K dash will be equals to concentration of A upon concentration of B. So here, if you compare the concentration, so can K dash will be equals to 1 upon K? Because this is B, concentration of B raised to the power upon concentration of A. Okay, so it will get reverse. Okay, it will get reverse. So can we write K dash is equals to 1 upon K? Yes or no? K dash is equals to 1 upon K. Because if you compare this, the concentration of A upon concentration of B, it is just reverse of that. I have just inverse this. Okay, concentration of B raised to the power A. So can we write K dash is equals to 1 upon K? Means the equilibrium constant for the reverse reaction is equals to 1 upon equilibrium constant for the forward reaction. Is it clear?
Yes, ma'am.
Now, so your equation. Now coming to the equation. So yeah, So this again, I'm just repeating this line, assuming that we initially started with HI, right? So this was the equation which is given in your equation is this reaction H2 plus I2, which gives you 2HI. But it has been mentioned over here, you have to assume that we initially started with HI. Okay, so we will reverse, we will write on the reverse reaction, just backward reaction, right? So how you will write on the reverse reaction? 2HI, it will get converted into a H2 plus I. That is a reverse reaction. Is this clear?
Yes, ma'am.
Yes.
Yes.
Okay. Now see, initially, if I write initially at the starting, okay, again try to understand this. Initially, when the reaction has not started yet. So initially, the concentration of HI, suppose it is A. Suppose it is A. The concentration of HI will be A. And now, initially, when the reaction has not started, there is no concentration. Okay, because the product has been not formed. The H2 and I2 is not formed initially. Only the reactant is there. The reaction has not started yet. So initially, when the reaction has not started yet, so the concentration of HI, which is reactant over here, so just assume it as a concentration A. Okay, and what about the concentration of H2 and I2? No, there is no concentration because the product to bana hi nahi abhi. The reaction has not started yet. So there is no product initially. Yeah. So now see, after some time, when the reaction like proceed like after to 5 to 10 minutes, okay, so concentration, I'm just writing the concentration at center, suppose. So you know very well when you start the reaction, okay, so concentration after some time, the concentration of reactant will decrease and the concentration of product will increase. Okay, products ban rahe hain, right? Products ban rahe and the reactants concentration has been used up to form the product. Okay, it's just decomposing because the concentration ye use ho raha hai, its concentration has been decreasing. Okay, the reactant concentration is decreasing and the concentration of product is increasing. Okay, when the reaction is going on. So after some time, what happens? Suppose X, okay, X concentration has been used up. X concentration, after some time, concentration, you know very well, concentration of reactant will reduce. Kitna reduce ho? Suppose let it be X. Okay. Suppose concentration, concentration has been used up. Okay, has been used up. So it is 2 moles. So I will write 2x minus 2x minus 2x. Why minus 2x? Because it's decreasing. And this minus this x. Okay, this x has been used. Okay, this x has been added in the concentration of product. So concentration of now at some middle or some at center. Okay. After some time, when the reaction is going on, after some time, the concentration of reactant will reduced. Okay, will reduced by minus 2x, and the concentration of product, which is H2 and I2, suppose it will become plus x and x. ओके, यहाँ से the reactant concentration decrease हुआ, कितना decrease हुआ? -2x, and this -2x is being used in the concentration, this concentration, it will become this concentration product and your those two products, H2 plus I2, okay, at the center. But at equilibrium, what happens? It will become, you will got the, basically आप क्या करोगे at equilibrium? Sum up. Okay, at equilibrium, what will be the concentration? So it will become A plus, just those का आप sum कर दो initially and this one. So it will become A minus 2x. And what about this? It will become X and X at equilibrium. Okay, is this clear? This point?
Yes, mom.
Yes, ma'am.
Everyone? If there is any doubt, you can ask. Okay. So this is at equilibrium. Now see, now just write down the equilibrium. And yeah, question, see the question. At equilibrium, the concentration of HI is mentioned. It is given, right? At equilibrium, the concentration of HI is given. So at equilibrium, A minus 2x will be equals to 0.5. Okay, because its concentration is given. Now, what you're supposed to do, now you can write down the equilibrium expression. What will be the equilibrium expression for this reverse reaction? It will be concentration of H2 into concentration of I2 upon your concentration of HI raised to the power 2. Okay, now see. H2, what is the concentration of H2? Now you will take the concentration, this equilibrium concentration. What is the equilibrium concentration? This one, X and X, right? So you will write, substitute the value X multiplied by X. And what about this HI? Okay, so HI concentration here is, it is equals to 0.5. It's given in the question, right? The concentration of HI is given. So you will write 0.5. Okay, now just solve this. Solve this. Yeah, one more thing. You can see, what is the value of K? This Kc value is for the forward reaction. This Kc, you can see this Kc value, the equilibrium constant for this reaction. The Kc value is 54.8, right? This is for the forward reaction, this one. But we have assumed this reaction according to the question as a reverse reaction. So for the reverse reaction, the K dash, okay, the reverse reaction के लिए K क्या हो जाता है? K dash will be equals to 1 upon K. Okay, it will got reverse. So here the K value, you can take the K value, the constant value for the reverse reaction will be 1 upon 54.8. Is this clear why I have taken 1 upon 54.8?
Yes, ma'am.
Okay, now you can solve this. 1 upon 54.8, it will give you x square upon 0.5 square. 0.5 square. Okay. Now, can we write this? X upon 0.5 whole square, it will be equals to 1 upon 54.8. Okay, now just take this square here. So x upon 0.5 will become equals to under root of 1 upon 54.8. Okay, so when you take the root, under root of 54.8, so it will become x upon 0.5 is equals to, so under root of 54.8, so it will become 1 upon 7.4. जब आप इसका under root निकालोगे, okay, using the long division method, you know very well, so you will get 7.4. Okay, now x is equals to, just cross multiplied, 0.5 divided by 7. Okay, just divide this.